So, good evening all. Till now we have studied about the temperature distribution inside the plane wall, hollow cylinder and hollow sphere. From now on we will take on our session to the next level and we will start talking about the critical thickness, which is very important topic in the case of heat transfer problems. So the thing is the critical thickness of the insulation. We will start talking about that. Critical or optimum thickness of insulation. It has two names: critical or optical thickness. Suppose there is some body like this. It has some surface temperature Ts and it is kept in ambient, which has a reference temperature as T infinity and H as heat transfer coefficient, and suppose that we insulate this body from the outer surface, right? We are insulating this body from the outer surface, same ambient temperature T infinity and heat transfer coefficient as, okay, this surface temperature is Ts, right? We are just, and by some means, because of some inside phenomena, sorry, excuse me. So because of some inside phenomena, its inner surface temperature is maintained at Ts. So, and to reduce the heat loss, we are insulating from outside surface. So this is the case, and let's calculate the heat transfer without insulation. This is the case without insulation. So it will go from Ts to T infinity, Ts minus T infinity, and there will be only one resistance as convection resistance as 1 by HA. So when we insulate, the extra resistance because of the conduction resistance of the insulating material extra material, the conduction resistance will also come into picture, right? So heat will now transfer from Ts to infinity, same temperature difference, but there will be, let's say, thickness L of this insulation. So L by Ka, the conduction resistance, and then heat will transfer by convection to the outside medium, and it will face the convection resistance of 1 by HA, right? So we see that if we put the insulation on the outside surface, resistance increases if we have the same area before insulation and out means after insulation. The because of this insulation, the total resistance increases. Total resistance increases. As a result, heat loss decreases. So we are insulating to remove the or to reduce the heat loss, right? And total resistance is what? Total resistance is summation of conduction and convection. Conduction and convection, right? So for same temperature drop, if we are insulating from the outside surface for this type of body, the total resistance will increase and heat loss will decrease. And that was the objective of ours, to reduce the heat loss by insulating the material. Okay. So the heat loss from any body in general is due to convection, and also radiation. But in this section we are neglecting the radiation, and also due to the insulation of low K value, which is the insulation material having low value of thermal conductivity, the thermal conductive resistance always increases because K is in denominator right here. So we are insulating the material with the material of low thermal conductivity, and because of that conduction resistance always increases for this type of material, not always, right? But convective resistance may or may not, depends on the H and also surface area. So convection resistance may or may not increase, depends on H, because it depends on H and surface area. It means total resistance may also increase or decrease, right? Because we are not sure that convection resistance will increase or decrease, so total resistance will also we can increase or decrease. Therefore total heat loss will also can increase or decrease due to this reason. So that's why we are here to study about the effect of thickness of insulation on heat transfer. So before beginning, so we will put some assumptions. I'm just writing all these assumptions. First is one-dimensional heat flow. We are assuming no internal heat generation in insulating material. Mind that, keep in mind, no internal heat generation in insulating material, right? 1D heat flow for plane wall and radial flow for cylinders and spheres. Right? And insulating material is homogeneous and isotropic, means there is no thermal conductivity variation with respect to at any point, and also with respect to direction, and also K value is constant with respect to temperature. Thermal conductivity value is constant, as we are assuming. Temperature drop is fixed. And heat transfer value is constant, it is not varying. Right. Next is radiation heat loss. As I said previously, radiation heat loss is neglected in this section. and thermal resistance of base material is neglected, right? What it means, it is very important assumption here. So let's say this is the cylinder we are insulating from outside of it, so it is insulate, so we are insulating this cylinder body from outside, right? This is insulation. So this is the base material, so we are not concerned about the thermal resistance of this base material, so we are not considering it. We are considering only this insulation thermal resistance, because it will be higher, right, as compared to the base material. And when we are insulating, there is some interface generated, and at the interface we know that contact resistance is also there, but we are assuming perfect contact. It means contact resistance between the two surfaces, that is at the interface, is 0.